Okay, guys. Okay, let's start with the May-June 2020 paper. Okay, so for question number 1, so we have this transition metal question. Okay, so an aqueous solution of cobalt 2 chloride. Okay, they have given that it contains this complex ion. Define the term complex ion. Now, when you want to define a term of complex ion, so do remember it's going to be a molecule, or it can be also ion. So in this case, we can say a molecule or ion. Better in this case, ion, right? So they say an ion. Okay, an ion. Okay, which has central atom. Okay, or ion. Yeah, in this case, I think better to say which has central ion. Okay, surrounded by ligands. Okay, so what are the marks? Okay, the marks they will like to see the central ion and as well the ligands. Okay, please take note of that. Now, sample of this okay, are reacted separately with aqueous sodium hydroxide and with excess of aqueous ammonia. So please remember, okay, that your cobalt cobalt ion, okay, the complex ion is always going to be pink in color. Okay, this is very, very important. It is pink in color. Okay, and then you are reacting with aqueous sodium hydroxide and aqueous ammonia. Now, if you react with sodium hydroxide, I have written over here, okay, you are going to get cobalt hydroxide. Now, cobalt hydroxide, okay, this is pink. Okay, the cobalt hydroxide is going to be blue precipitate, and this precipitate, when you warm it, okay, if let's say you are using sodium hydroxide excess, okay, if you warm, it will change into red. Okay, but in this case, okay, I'll just leave it over here. This one is going to be extra notes for you. Okay, but to answer the question over here, okay, the reaction with aqueous sodium hydroxide, the color and state the cobalt containing species. Okay, the color is going to be blue. Okay, and then the state is going to be precipitate. So they want to know whether it's going to be blue precipitate or blue solution. So in this case, this is precipitate. And then the ionic equation, so you just write down COH2O6, 2 plus, okay, plus OH minus, okay, to give you, because I don't want sodium hydroxide, we want ionic, okay, so to give you cobalt hydroxide, solid, okay, plus all the remaining H2O has been removed, okay, so it's going to be 6 H2O over there. Okay, this is going to be everything that is going to happen, but just check, okay, OH you need 2, so you need to put 2 there. Okay, so this is going to be your ionic equation. Now the type of the reaction that is happening, because there is going to be, this is aqueous, okay, this is aqueous, this is solid, and this is liquid. Because there's a solid that is being formed, so you just say type of reaction is precipitation. If you want, okay, if you want, this is also what we call as acid-base reaction, to give you salt and water. If you want, you can also do that, okay, but I think the best way is to represent it as precipitation reaction. Now the reaction, okay, the reaction is going to react with excess aqueous ammonia. Now the excess aqueous ammonia, so I have written over here, if you have ammonia, okay, all the ammonia ligands, okay, will replace, okay, the water ligands. Okay, all the ammonia ligands will replace the water ligands. So you are going to have the color that you are going to actually observe over here. Okay, the color that we are looking is going to be a blue solution. Okay, so it's a blue solution. It's not going to be a precipitate. So please remember this. Okay, it's going to be blue solution. And then the ionic equation is going to be, you are going to have something like this. 6 ammonia, you are going to get cobalt. Now, Jody, can you tell me whether what is going to be the charge? Okay, is the here, why the charge? Okay, you can see here, why is going to be 2 plus? Why is not going to be neutral, Jody?
And H3 0, yes.
Yeah, and to be exact, H2O was 0. Okay, H2O was 0. So it's cobalt 2 plus. So when you replace with NH3, yes, NH3 is also 0. So the 2 plus will stay. Okay. So this one, please take note. Okay. So this reaction is going to be exchange of ligands. Okay. The ligands that are involved will be water and ammonia. So we call it as ligand exchange. Okay. Done. Now, furthermore, okay, related to cobalt, okay, when concentrated hydrochloric acid is added to a solution, okay, of cobalt this, okay, a blue solution is formed, okay, and the following equilibrium is going to be established. So you see here, when you are adding with sodium hydroxide, you are going to get a blue precipitate. When you are adding with ammonia, you are going to get a blue solution. When you are adding with the hydrochloric acid, you are going to get a blue solution. So please remember all this. Okay, in this case, use LCP principle, okay, to suggest the expected observation when silver nitrate solution is added. Now, silver nitrate, they are going to react with the Cl minus to give you silver chloride and precipitate. Silver chloride is a white precipitate. So in this case, what happens here is going to be you are removing the Cl minus. If you are removing the Cl minus, what happens? Okay, according to LCP, you do not want the Cl minus to be removed. So you need to counter react the situation by shifting the position to form more Cl minus. So the position of the equilibrium will be shifted to the left. So here they say suggest what is going to be expected observation. One observation is going to be because silver chloride is being formed, you can just say a white precipitate is formed. Okay, that's going to be the first one. Second is going to be, we know this is going to be a blue solution. If it is going to move to the left, the blue solution is going to be not going to be formed. You are going to form more of this. Okay, and this color earlier I mentioned to you. Okay, cobalt. Okay, in this form they always exist in pink solution. So you are going to get the solution to turn to become more pink. So you can actually say the solution change from blue to become pink. Okay, the solution change over there. And then you can say also, okay, because it's 2 marks, okay, you can also say the position of the equilibrium is shifted to the left. Okay, position of the equilibrium shifted to the left, which will actually explain this part, okay, if you want. So, but any of the two responses over here will be given the marks. So any two, okay. So you need to explain. So I think when it comes to explaining, you need to still mention about this. Okay, you still need to mention about the position of the equilibrium, what happened because of the white precipitate is formed. You are going to reduce the Cl concentrations, a chloride ion concentration, and then the position will move to the left. So you don't have any choice. Okay, so you still need to actually write down. Now for this one, okay, because we are discussing about cobalt, okay, ions, okay, I still want you to go and refer to my video, okay, on this ligand substitution for complex transition ions. Okay, so this is the exact title. Okay, maybe later I will actually put it, if I upload this video, okay, then I put it in the description, or I will send it in the WhatsApp group as well. Okay, I have discussed in the, I think, 10 minutes video, okay, about all the equations involved for the ligand substitution. So in this particular question, we have discussed 3 equations involving cobalt. So you still need to actually learn about copper. Okay, so please watch that video about copper. Okay, so in this case, you can see, okay, how many marks given just for this. Okay, you see 1, 6, okay, and 2. Okay, so you are roughly looking at 9 marks, and they didn't stop over here. Okay, if they want to continue with copper, they can continue and asking more. Okay, but instead of doing that, they straight away go for introduction to organic chemistry, or more towards your A2. If you look at it, it's going to be stereoisomerism for complex ions. So they ask you, okay, they mentioned that this complex can show stereoisomerism, complete 3-dimensional diagram to show 2 isomers, okay, of this. This one is going to be slightly different than what we normally do, because it's going to have three ligands each. So this one definitely the shape is going to be octahedral. Okay, that is confirmed. Okay, but the way that we draw, okay, so if I just put it in this way, so if I just put it here, okay, if I put it like this, okay, I am going to expect to see, okay, so something like what we don't have any choice like putting in. If you have NH3 2 Cl4, then it's easier. Okay, it's easier. I can put the ammonia up and down. Okay, but in this case, it's going to be slightly complicated. So I will actually put the ammonia here, NH3 here, and then ammonia here. Okay, and one of the ammonia needs to be put somewhere. Okay, so you need to decide, okay, where do you want to put. Okay, so in this case I will decide to put the ammonia maybe somewhere here. Okay, so I will put it here, and then the remaining Cl I'm going to put them over here. Okay, so this one is going to be, they are appearing side by side to each other. Okay, if I actually put it, okay, ammonia here, okay, and then Cl here, if I put, okay, the remaining Cl, okay, if I put one Cl here, another Cl there, and then ammonia here, another ammonia here, you can see that, okay, what happens here. Okay, I think even it will be better if I show it like this. Yeah, I think if we can actually show similar to this, so maybe I'll actually show somewhere here. Hold on. Yeah, the idea is to show whether they are cis or trans. So I will actually put it here, NH3 and then Cl. So I will put the ammonia side by side here, and then Cl side by side here. It's much more easier to see. But if you look over here, there is two ammonia here, and then one ammonia across. Okay, two chlorine, another one across. So this one is going to be more towards cis and trans. Okay, they didn't ask. Okay, it's a bit complicated. So the type of isomerism is going to be geometric isomerism, or you can actually say cis or trans. Okay, so this is how you draw. Now, one thing that I want to highlight over here is going to be the way you show. Okay, the way you show. Okay, this is, it's okay when you just simply do it for your revision, but now I think we need to practice about how to show them. Okay, if it is coming out, okay, from the, from your iPad or coming out from the paper, okay, it's supposed to be something like this, and then, okay, replace with the dotted line. Okay, so probably something like this. If you can just put, okay, you can refer to the marking key. So this is going to be the type of stereoisomerism that it can form. Okay, I'm very sure we have discussed this question before last time. Okay, please take note as well. Okay, this is going to be something that you need to see or visualize. Okay, so the best way is to look at it. You just put ammonia and Cl here, ammonia and Cl, and then you put all the ammonia at one side here. Okay, so they look like cis. Okay, so here if you put one, okay, here, and then put them at across, okay, that will look like trans. Okay, now let's continue. Compound X is going to be tetradentate. Tetradentate means they are going to able to form 4 bonds. Okay, 4 of the lone pair can be donated, okay, to the metal ion. So suggest why one molecule of X can form 4 dative bonds. So when I see this, there's nitrogen. Nitrogen has one lone pair, one lone pair, one lone pair, and one lone pair here. So they have, okay, nitrogen, okay, 4 nitrogen, 4 lone pair, okay, which is going to be available for bonding. So that will be the answer for this. Okay. The next question is, okay, this compound, okay, they react with cobalt 2 ions, okay, with 1:1 ratio to form a new complex ion. So construct an equation for this reaction. So I've done it earlier, okay. So what I feel like cobalt, okay, cobalt, you are something similar with the previous example. This cobalt, the 6 water will come out. So water is going to be neutral. So it's going to be still CO2 plus, and then going to be replaced by this tetradentate ligand. This tetradentate ligand is also going to be positive, zero charge. Okay. So when they come in, okay, they are just going to join this, and do not forget about the 2 plus. The 2 plus is going to be staying because why? This is going to be neutral. So the charge is going to be zero. So when you add, okay, you are going to get this, and then the 6 moles of water will come up over here. So that's going to be the equation for this reaction. So this one maybe takes time to visualize, but do remember they are going to form 4, okay, 4 bonds, okay. So cobalt, okay, then straight away 4 bonds. There's no need to show, okay. But the important thing is when this 6 moles of water goes out, the charge 2 plus stays, okay. And then when they come in, the charge also stays the same because they are neutral. So if you actually put this as without the charge, you are missing that 1 mark, okay. You won't get that 1 mark. So you see how they have actually done this question, okay. They have given you, asked you about complex ion. They tested you on the equation, okay. They have tested you on the stereoisomerism. I think they've given something a little bit tricky over here for this particular paper. And then they ask something simple, okay, but you see why and so on, okay. They just want to test your basic understanding of this, and as well as this, okay. In future, don't be surprised if you have with the ratio of 1 to 2, okay, or something for different ligands. So this is something that we need to also expect, okay. So this one, please take note. This is some of the ways that they can actually ask question, okay. The next question is going to be question number 2, which is very, very important. Yeah, this is what I want to actually highlight every single time when we learn lattice energy. When you revise your lattice energy, this is something that you really, really, really need to take note, okay. Please remember this, okay. So describe and explain the trend in solubility of the group 2 hydroxide down the group. If they ask you this question in your AS, they will just say describe or state the trend of solubility of group 2 hydroxide. Your answer will be the solubility will increase. That's it. They will not ask you to explain. This is only going to happen in paper 4, okay, which is going to be your knowledge about lattice energy, hydration energy, and solubility. Okay, so in this case, okay, please remember this. Okay, in your AS, we have learned that solubility of hydroxide going down the group, solubility increases. Okay, but in sulfates, okay, sulfates going down the group, solubility decreases. How to remember that? Okay, just remember magnesium sulfate and then barium sulfate. In chemistry, if you do not know what is going to be the color of barium sulfate and what is the state of barium sulfate, then something wrong with you. Yeah, so please take note. All chemistry students must know that barium sulfate is a white precipitate, one of the basic requirement for a chemistry student to know. And do remember, if this is white precipitate, of course, the one that is top, which is going to be magnesium sulfate, they are aqueous. So from aqueous to change into white precipitate, you can clearly see that there is going to be decrease in the solubility. Okay, they are going to form precipitate. So please remember this. This is going to be in your AS. Now, when they ask you to explain, okay, now we focus on the OH. They say explain the trend of the solubility of group 2 hydroxides down the group. Now, how to explain? Okay, this is related to the formula. Okay, but explaining, I think no need to use the formula. Okay, this one is going to be what I told you to remember. Let the soul go and hide. Okay, if you can remember that. Okay, lattice energy, let the soul go and hide because they are going, so it's going to be negative. I put it over there. Okay, but whatever it is, okay, this is going to be the relationship between them. Okay, or if you just want the solubility, the solubility is going to be lattice plus hydration. Okay, do remember lattice energy and hydration, they are both negative. Okay, they must be negative. Okay, lattice energy and hydration, they are negative. But the solubility, okay, the solubility is going to be, can be either positive or negative. If your value is going to be negative, okay, it's going to actually tell us that this is going to be soluble. Okay, this is very important. If your enthalpy of solution is going to be negative, that is going to tell us about, okay, this is going to be soluble. Okay, please remember this. So now how do I relate with this? Okay, going down the group, okay, you are going to have, okay, your lattice energy and your hydration, because of the size that is increasing, the ionic radius that is increasing, they will make the enthalpy of lattice energy and the enthalpy of hydration to become less exothermic. Okay, they are going to become less exothermic. And which one changes more, or which one become more or less exothermic? Okay, so in this case, okay, you need to compare lattice or hydration. In this case, for hydroxide, the lattice energy changes more. Okay, the lattice energy changes more. Explanation is basically M2 plus, okay, is bigger than OH minus, okay, all this kind of explanation. But again, if you want to memorize, it's up to you. Okay, lattice energy changes more. If the lattice energy changes more, according to this equation, okay, if you know how to apply this equation, it's very good. If you just want to memorize, it's up to you also. Okay, lattice energy changes more. If that happens, okay, if lattice energy changes more, which is going to become less exothermic, your enthalpy of solution will automatically become more negative. Okay, it's explained using this equation. Now, when that happens, okay, it is going to tell you that the solubility will increase. Okay, solubility is increasing. But of course, we are not there to just write down our answers. Okay, we want to learn. Okay, so how if they ask this question related to sulfate? Now, sulfate is going to be, and your sulfate solubility will actually decrease down the group. But it's going to be, every explanation is going to be opposite to what we have explained for hydroxide. Okay, the solubility of sulfates going down the group, okay, will actually decrease. Why? Okay, the lattice and hydration, okay, the enthalpy of hydration, they are going to become less exothermic. That is actually the same for hydroxide and sulfate. But which one changes more? If your hydroxide, the one that changes more is lattice, in this case, the hydration changes more compared to lattice. Why? This is again related to the size. SO4 2 minus is actually bigger compared to M2 plus. Okay, but in this case, the hydration changes more. And what happens when the hydration changes more? Based on the equation that we look over here, what happens? Your enthalpy of solution becomes positive. And when this becomes positive, okay, you can say that this is going to become less soluble. Okay, less soluble. So this is something that you need to remember. So I came out like maybe how to actually remember or something. I was thinking, okay, hydration, if you're talking about hydroxide, then I can actually remember lattice changes more. If you're talking about sulfates, then I know that hydration changes more. Okay, is there a way to make it simpler? Okay, so I came up with this simple SHL. So maybe how to apply this SHL. So basically, if you have sulfate, okay, sulfate, what happens? Sulfate, your hydration, okay, changes more. Okay, if you have sulfate, hydration changes more. If you have hydroxide, okay, if you have hydroxide, then your lattice energy changes more. Okay, you can actually use this method, and I'm going to use this method also to remember. SHL. Okay, this is going to be sulfate. Okay, then hydration. If I'm using for hydroxide, then I'm going to say this is going to be lattice. So this is something that I'm going to use as well. Okay, next, okay, group 2 hydroxides decompose on heating to give you corresponding metal oxide and water vapor. So here they are asking you which one will decompose easily. Okay, with magnesium hydroxide or strontium hydroxide. But again, okay, in your AS, let's actually have a look at AS, your group 2 also. Okay, you're related to your thermal stability. Now, here they are asking about hydroxides. Okay, but we have also learned about nitrates and carbonates. The same explanation also. Okay, thermal stability for nitrate, carbonates, and hydroxide going down the group. Okay, thermal stability, okay, it depends on the polarizing power. This is only in your A2. So if you have a better polarizing power, okay, this polarizing power comes from positive ion. Okay, if the positive metal ion, okay, is small and has more charge, it means they have higher charge density. So if they have higher charge density, they are able to attract the electron cloud. So we call it polarizing the anion. Okay, so they will actually polarize the anion. So what happens? This anion, NO3, CO3, or OH, they get polarized. Okay, when they get polarized, the electron cloud become distorted. So when they become distorted, the bonding between nitrogen and oxygen, the bonding between carbon and oxygen, the bonding between oxygen and hydrogen will become weakened. If that becomes weakened, it's going to be easier to decompose. Okay, you do not need to have a lot of temperature to decompose them. So it means that in order to do that, okay, the metal cation must be small. Okay, so the top one must be is the smallest one. If you look at group 2, if you go up, go down, then the size becomes bigger. So it means that it's easier, okay, to decompose. It means you require less temperature to decompose at the top, and you require more temperature to decompose at the bottom. So it means that, okay, thermal stability going down the group, okay, is going to become more stable. Okay, they are going to become more stable. Thermal stability increases down the group. Let it be nitrate, let it be carbonate, let it be hydroxide. Okay, and why? Okay, now it's actually related to the polarizing power. But have a look at the marks. Only 2 marks are given. So first, you need to answer the question. Which one will be easier to decompose? If I look, magnesium is at the top, strontium is at the bottom. So in your periodic table, so magnesium is going to be will have more polarizing power. Okay, then it will be able to polarize OH, and then OH will be broken easily. It will be decomposed at lower temperature. So that is what is playing in my mind. So what do I actually put it over there? So the answer is magnesium hydroxide. Okay, what else you need to put? Very important. When they say explain, you explain in detail. Okay, what happens? Why this one has uh, more, like for example, polarizing power? I cannot simply say they have more polarizing power. You just need to explain. Magnesium 2 plus, okay, is smaller. Okay, magnesium 2 plus is smaller. Okay, of course you don't compare with the charge, because the charge is the same. So you say because of that, okay, your charge density, okay, not the charge but charge density. Your charge density is charge divided by radius, okay, ionic radius. So charge density is going to be more. Okay, if your charge density is more, okay, so Mg2 plus is able to polarize, okay, hydroxide, okay, and weaken the bond of O and H. Therefore, it's easier or requires less temperature to decompose. Okay, so this is important. Okay, why? Because when you say Mg2 plus here, when you write down, please write down ionic radius. Okay, I don't actually write everything, so I just put ionic radius is going to be smaller. That's going to be the important mark that they mention in your marking key. They want to see the ionic radius and they want to see the charge density. Okay, and then do we need to mention how it will form a bigger or smaller cation? Yes, okay, yes, because it's actually no. When you are talking about why the ionic radius is smaller and so on, no need, Gabriela Nicole. So generally, it is understood. It is at the top. They have Mg2 plus. Okay, they have less number of shells. If you mean that you want to talk about the number of shells, no need, because it's only 2 marks. Okay, because we know for sure 1 mark is given over here. So another one more mark is actually based on your explanation. So I don't think so to explain the ionic radius is going to be important. So, but it's important to say that the ionic radius is smaller, charge density is more, able to polarize and weaken the bond. Even if you look at this, weaken the bond, it's not even in the marking key. Okay, but it is better. Okay, it is better to write it down because these marks can be fluctuated. Okay, if they decide to give you 3 marks, okay, instead of 2 marks, then the weakening the bond will be one of the key points that they will look in awarding you the mark. Okay, so it means polarize and then weaken the bond. So please actually take note as well. Okay, but in this case, no need. Okay, no need, but everything depends on the marks given. Okay, if they give you 4 marks, yes, please explain about the number of shells. But I think in paper 4, they are not going to focus on the number of shells. But in AS, yes, you need to talk about shells. Okay, why the ionic radius is getting smaller and so on. So that is important. Okay, it depends on the level also. Now, if you move further, okay, so the number 3, okay, the overall reaction for photosynthesis is shown. They have given you one half equation over here. So they are asking you to use these equations to deduce the half equation for the reduction of carbon dioxide. So I know that, okay, this is the full equation. Okay, I know this is the full equation. So how did I start? Okay, so I just write down, like, for example, H2O, okay, to give you O2 plus 4H plus 4 electron. Then based on the, okay, just ignore this first, yeah. Based on the question, okay, I know that they want to reduce carbon dioxide. So it means that carbon dioxide must be reduced. Reduce means gain of electron. So it must be gaining the electron. And I know that when I add these two equations, I need to get something like this. So I have carbon dioxide. So I need C6H12O6 because it's not available in my first equation. So I know, okay, maybe it will give you C6H12O6. Okay. So these are the information roughly I have for now. Okay. But what I notice also here, okay, is going to be, I do notice, okay, when I have this oxygen, okay, the oxygen in this case, when they are oxidized, okay, here all the oxygen I think will go here. Okay, so the oxygen is coming out from here, okay, which is going to be the from the water. And I notice from the entire equation there's 6O2. Okay, if I notice that there is going to be 6O2, so what I do is I need to make sure that all of them have 6. So I end up, okay, by multiplying everything by 6. Okay, so I multiply by 6. I multiply by 6. I multiply by 6. Okay, and it is important to eliminate all the electrons. Okay, so 6 times 4 is 24. Okay, so it means I know that this is going to be 24 electrons. I need to get that eliminated. And there is no H plus in the main reaction. I have H plus here. So it means that there is no H over here. There is H here. So it means that this H plus must be eliminated. So 6 times 4 is 24 H plus. So automatically this one will be 24 H plus, must be eliminated. So I just put 24 H plus. The rest, I just need to double check everything is balanced or not. Like for example, when I look at carbon dioxide, okay, there's 6. So of course I need 6 carbon dioxide over here, okay, to balance the equation. And then what else I see is going to be, I notice that, okay, water, okay, water is going to be here. When I times by 6, I'm going to get 12 water, okay, but overall I'm only having 6 water. So it means that you need to actually have formation of water, because if you count, that is going to be to tell us that the water is not going to be enough here. So there's going to be water that is going to be given. Okay, so that water, okay, is going to be, because 24H plus, you only have 12 hydrogen. So here there will be water that is going to be formed. How many? So it means I need to actually form water, so that when I deduct the from 12 H2O, I'm only going to have 6 H2O. So the best way is to put 6 H2O here. So I get something like this. Okay, so this is going to be helpful to tell me that this is going to be my, okay, half equation. So this is how I came about with the formation of half equation. So I need to write down, okay, or every single detail that they have mentioned over here is going to actually help you in coming up with this. If they need you to refer to the data booklet, they would actually tell, okay, refer to the data booklet. So this one, you don't waste time by looking at the data booklet. Okay, it's not there. Okay, now here, but don't expect to actually they tell you every single thing, especially when it comes to measuring standard electrode potential. Okay, sometimes they will tell you refer to the data booklet, but it is understood if they are asking you to calculate, okay, standard electrode potential, you need to refer to the data booklet. So let us see whether they say refer to the data booklet. Yeah, you see, it's good. Okay, it's good that they are asking you to refer to the data booklet, but not all the time. Okay, it is understood. I think certain cases it is understood you need to use data booklet. But in this case, draw a fully labeled diagram to measure the standard electrode potential of O2 in a half equation under standard condition. Include all the necessary chemicals. Okay, so you need to measure standard electrode potential of O2, okay, in half equation 1. So it means you need to write the entire thing. Yeah, so there will be, we are using the hydrogen cell, so it's going to be something like this. So you need to still give the hydrogen. So hydrogen will come in here, and then here will be, please draw nicely here. So here will be H plus, this is platinum. So this will be H plus 1 mole per dm cube. Then voltmeter to measure. Then again, this is going to be related to half equation 1. So water and oxygen. So you are going to actually relate to oxygen. So again, gas. So you still need another platinum here. So again, H plus 1 mole per dm cube. This one, oxygen. So this is going to actually help us to actually find out what is V. So here from the cell drawn, okay, we know that hydrogen here, hydrogen cell is going to be 0. Everyone should know this, okay. Then you need to actually make sure, okay, do not take the wrong, okay, do not take the wrong equation from the data booklet. Okay, the data booklet, we want the information related to water, H plus and O2. Okay, so you can refer to your data booklet. Okay, that will give you positive 1.23. So I can show you, okay, the data booklet, so that you don't actually make the same mistake, because if you look at the data booklet, there's so many things related to water and O2. Okay, I'll show you. Okay, this one, and then there's also this one. Okay, but the one that this one, sorry, this one H2O2. This one, okay, it is important to select which one we want. So we wanted to actually relate it to O2 and H plus. So we want to select the 1.23. So do not accidentally choose something that we don't want. There's so many other things as well. Okay, so you need to refer to what we want. So I want the 1.23. So if I put the 1.23 over there, so this is going to be the E cell. Okay, automatically this is not 0.4, yeah. So this one will follow this one. Okay, 1.23. And then the identify the positive electrode. This one, please remember, if this one is 0.00 and then 1.23 positive, okay. So of course, this one I told you, the one that is more positive will go to the right. So this one will go to the right. So if you go to the right, okay, the equation that I am actually going to use is this one, O2 plus 4 electron. Now, this is going to be plus electron. If you are gaining electron, is it positive terminal or negative terminal? Charlton?
Negative.
How come? Okay, you study physics also, right? If it is terminal, yeah, okay, terminal, if it is releasing electron, then it's going to be negative terminal. So in this case, this is going to be accepting the electron because you are following this direction. Okay, so if you are using up the electron, this is going to be automatically is going to be a positive electrode or positive terminal. So O2 is going to be the one that has the O2 is automatically the positive terminal. Please take note of this. Okay, negative terminal is the where the electron comes out. So the electron will go here. Okay, so this is negative terminal, the hydrogen. So electron will go here, and then they will receive the electron over here. So that's going to be positive electron. So please remember that that thing is very important. So now it's already 10. So we only managed to discuss 3 questions. Okay, let me stop. What we're going to do is we are going to look into the how amine is going to be formed. So to be exact, there are 3 methods of forming amine. You can actually have a look at the notes that I have given you. So one of the way is going to be from amide to become amine. Okay, the only way that you can do is going to be by using a very strong reducing agent, which is going to be LiAlH4, okay, in dry ether. So the reaction one suggests region and condition. Okay, to suggest the region and condition, the region is going to be LiAlH4. Okay, so the condition in this case is going to be, you can actually put in dry ether. Okay, in dry ether. And then I don't think so there is a need to warm them. Okay, but if you want to write down warm, it's okay. Okay, but these 2 will do. Okay, reaction 2. Okay, if for reaction 2, how do we actually change halogenoalkane to become amine? Now this one you need to be very careful because there are other reactions involving that reaction, halogenoalkane. One is going to be if you are using KCN. Okay, KCN in ethanol, then after that you reflux. Okay, you are going to get something that have additional number of carbon. So you can see here, okay, I do not need additional number of carbon. Why? Because carbon, 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 and carbon. There is no increase in number of carbon. If there is an increase in number of carbon, then you need to use this method. Okay, you need to actually add with KCN in ethanol, then reflux. After that, you are going to actually reduce them. There are 3 ways to reduce them. Okay, you can actually use LiAlH4 in dry ether, or you can use hydrogen in nickel, or you can use sodium in ethanol. Okay, so all these are if you are going to add number of carbon, but same, it's also production of amine. So that is going to be something that is going to happen here if you have more number of carbon. But in this case, because there is no increase in number of carbon, so it is enough to just react with hot ethanolic ammonia. Okay, and then this one is not mentioned in the textbook, but it is mentioned in the marking key. So we will actually just learn and just put everything in together. So here, okay, the reaction 2, it must be hot ethanolic ammonia. Okay, hot ethanolic ammonia, and you just put under pressure. So it means extreme condition. So you want certain condition, which is going to be the halogenal alkane must be reacting with ammonia under extreme condition. It must be hot. It must be also has high pressure. Then you are going to get amine. Okay, so that is going to be the reaction. So the type of reaction in reaction 1 and name the mechanism in reaction 2. So the type of reaction, okay, so you can see here, amide to become amine, you are using reducing agent. The type of reaction is reduction. So you see the term that they are using, type of reaction, mechanism of the reaction. Mechanism is going to be different from reaction 2. Okay, what kind of mechanism that we are talking about? Okay, this mechanism involving any reaction about halogenal alkane and alcohol. Okay, please remember this. Halogenal alkane or alcohol will involve nucleophilic substitution. Okay, nucleophilic substitution. So nucleophilic substitution, they have SN1 and SN2. Okay, please go and read about this, SN1 and SN2. When do we use SN1 and SN2? Okay, what kind of method? Are we going to use carbocation, or are we going to use transition or intermediate? So to answer that, okay, there is a simple way to actually remember that. So do remember SN1, it's going to actually work for what kind of halogenal alkane? So I remember tertiary halogenal alkane, something opposite. If it is SN2, then it's going to be, I'm going to talk about uh, primary halogenal alkane. Okay, so I just remember in this case. So SN1 is going to be tertiary, SN2 is going to be primary halogenal alkane. So if you have tertiary halogenal alkane, it means there is a formation of tertiary carbocation. So if you have tertiary carbocation, according to Markovnikov rule, if you have tertiary is much more better. Okay, it's more stable. So tertiary, you are going to have SN1 is the formation of carbocation. So this one SN2 is going to be, you don't want primary carbocation because it's not stable. So it's going to be involving transition or intermediate. Then you can actually use this information, okay, to actually draw the mechanism of the reaction. So this is going to be roughly how you differentiate SN1 and SN2. Okay, so how to draw the using curly arrow diagram and so on. I've done another video on this. Okay, please go and have a look in the YouTube. I have uploaded, okay, under SN1 and SN2. Okay, let's actually move on. Now, benzene, okay, they react with bromine in the presence of aluminum bromide catalyst. So basically, you see benzene, they react with bromine with the presence of halogen carrier. Okay, if you have halogen carrier, so they are going to actually react where they are going to be attached to the ring. Okay, so it's going to be what we call a substitution reaction, which we call it as a nucleophilic nucleophilic. Is it nucleophilic substitution or electrophilic substitution? Let me check. Okay, Jody, benzene, will they actually undergo nucleophilic or will they undergo electrophilic?
Electrophilic.
Why, Jody? How to remember?
Have double bond.
No, don't actually think about double bond. Okay, in benzene there is no double bond. So we always think that the benzene ring has a delocalized electron. So they always rich in a lot of electron. So they are having high density of electron. So electrophile loves electrons, so they will go there. So that's why it's called electrophilic substitution. Okay, is that clear, Jody?
Yes, sir.
Okay, please remember this. Nucleophilic, okay, when it comes to nucleophilic, please remember if you are talking about nucleophilic substitution, remember SN, nucleophilic substitution. We just learned about this. Nucleophilic substitution is going to be for halogenoalkane and alcohol. Okay, and then another one that we need to actually remember is going to be a nucleophilic addition. Nucleophilic addition is for carbonyl compounds. Okay, carbonyl compounds, aldehyde, okay, ketone. That's going to be nucleophilic addition. Okay, please revise more. Electrophilic addition, that's going to be double bond. So Jody, the one that you mentioned about double bond, that's electrophilic addition. Okay, electrophilic addition. So this is electrophilic substitution. Okay, now explain why no addition takes place. Now to answer this, you need to actually answer in a proper way. Okay, we need to actually tell, okay, if there is addition, then the product that they form is not stable. Okay, why? Because when we say stable, we say that, okay, when the electrons, okay, when they become delocalized, okay, when they become delocalized in the ring, then the entire molecule is going to be stable. Like for example, if I have a benzene, then I add Br over there, the electron from the Br will also enter the ring. Okay, they will be going into the ring, and then those electron is going to become delocalized within the ring. So in this case, why this reaction happens? Because the structure that whereby the electron being delocalized is more stable. So you just need to actually explain the substitution, okay, product is stabilized by the delocalization of the pi electron. Okay, the substituted product is stabilized, okay, because or by delocalization of 6 pi electrons, or pi electrons will do. Okay, so there is going to be, or if you want to actually say, if the, let's say there is addition, then the addition product is not stabilized by delocalization of pi electrons. You can refer to the marking key. Okay, but this one I want you to remember. Okay, why this is more stable? Because the substituted product is stabilized by the delocalization of the pi electrons. Okay, let's move on. Now, AlBr3 reacts with bromine to generate an electrophile. Draw the mechanism of the reaction between benzene and Br plus ions. So basically, this is going to be electrophile. So you do not need to write down, okay, what is going to be the equation here, but I think they ask you to write the equation in the third part. Write an equation to show you how, okay, how AlBr3 catalyst is reformed. This is afterwards. Okay, so if let's say they ask, okay, it's supposed to be Al. Okay, let me actually charge. Okay, it's supposed to be AlBr3. Okay, when they react, okay, when they react with Br2. Okay, this one, please remember how the reaction actually takes place. There is going to be, can you guys hear me? Let me see who is not muted. Okay, so okay, let's continue. Now you can see here, okay, you can see that AlBr3, okay, they are going to react with Br2, okay, because okay, there is going to be some sort of a what they call they will, when this AlBr3 comes closer to Br2, the electron, okay, they are going to induce the electron to go more to one side, okay, where they are going to have heterolytic fission. This one It's not required for now. Okay, basically it's supposed to be there will be heterolytic fission taking place. So you are going to get AlBr4 minus, okay, plus Br plus. Okay, you are going to get this. So this is the one that we have over here, the electrophile. If they ask you to write down that, okay, then you write down that equation. So, but now draw the mechanism of the reaction between benzene. So I just draw benzene, okay, with Br plus, okay, Br plus. What I draw is going to be the curly arrow diagram. Please see from where to where it's coming out. Okay, so you are going to have, okay, something like this. Okay, this one from here to here plus, and then you have H, you have Br. H was already there in the since the beginning. So now this is going to actually go and go inside here. Okay, the electrons. Okay, so there is going to be another heterolytic fission is going to happen, whereby you are going to get this structure, the bromobenzene plus, okay, H plus. Okay, so this H plus is the one that will be actually used over here, which is going to be the H plus. Okay, when you react with the here, okay, when you react with AlBr4, okay, so what happens is going to be you are going to get AlBr3 plus HBr. So you are going to get the catalyst being reformed. Okay, this is I think we already discussed so many times. Okay, you need to actually know about this. Okay, you must know about this. Okay, very, very important. Okay, let me share the screen again. Yeah, so it's not okay, it's appearing slowly, very slow. Okay, so let me actually move on. Okay, suggest why, okay, bromination of phenol occurs more readily than the bromination of benzene. So to suggest why, maybe Shane, can you actually tell us why bromination of phenol is more readily happen than bromination of benzene?
Because lone pair of oxygen is delocalized into the ring.
Okay, so basically phenol, okay, phenol have this OH, okay, the lone pair, okay, the lone pair of electron at, of the oxygen, they will become delocalized into the ring or delocalized into the pi system, okay. So because of that, okay, you are going to have more electron density, okay, there will be more electron density in the ring. So if there is going to be more electron density, so it is more available to be for bonding with the electrophile. Okay, so that's going to be 2 marks. Okay, so if I see the marking key also, the what are the things you must mention is going to be the lone pair of oxygen is delocalized into the ring. Okay, so that is the first mark that is going to be given, but you need to actually explain one more. Okay, phenol now has higher electron density in the ring available for bonding with electrophile or something like that. Okay, they also mentioned phenol can polarize or induce a dipole in Br2. I don't think so. That is, I don't teach you about that. So basically, the important thing that we need to think about is going to be, okay, when the lone pair become delocalized into the ring, okay, now you are going to have more electron density. Okay, so if you have more electron density, so it is readily available to be bonding with the or reacting with electrophile. Therefore, okay, because we are talking about bromination, we are talking about electrophilic substitution. So it is related to that. Okay, so 2 marks is done. Now, C, okay, this one I have discussed earlier sometime back. Okay, there are 4 different carbocations with the same formula, C4H9. One structure is given in the table. So they are asking you to draw the structural formula of 3 other carbocations. So do remember they want you to write the structural formula. So the way that I written stuff over here, I think because I want to visualize, so I actually put it in form of displayed formula. Okay, so but this is not going to be accepted, okay, because you want structural formula. So here when I notice here, I noticed that, okay, you have 4 carbon, okay, and then this carbon, there is positive over there. So if I draw, like, it will look like CH2, and then this is positive, the rest C3H7. So I can see that, okay, this is going to be a primary carbocation. Okay, I can see it's going to be 1R primary carbocation. But can I actually come up with different kind of carbocation? So using the same method, okay, if I have C and H, okay, C and H, if I can actually break that C3H7 into like CH3 go here, CH3 go there, this is going to be another carbocation, but again, it is still going to be a primary carbocation. Primary, this is also going to be a primary carbocation. Okay, one of another possibility. So how do I write it down? Okay, I write down, okay, CH2 plus, okay, then CH3 2. So it means I write C, maybe H, then bracket CH3 2. Should be okay like this. Okay, so you are going to have something like this. Okay, so this is going to be primary. So if let's say let's look at structure 3. Okay, what else can I form? Okay, maybe now instead of putting all the hydrogen there, maybe one of the hydrogen I change it into CH3. Okay, I put CH3, then I still maintain the hydrogen I put over here. So I need to have 4 carbon. So 1 carbon, 1, 1. So 4 carbon. So if I have this, okay, this is going to be, if I just simply look, this is going to be one R group, another R group. So it's a secondary carbocation. Okay. So how do I write down, okay, in form structure formula? So I will write down maybe CH3, CH2, then this C is bonded to H and also CH3. Okay, and then I put plus, maybe I can put the plus here. Okay, this carbon. So this is going to be another one more. And then structure 4, okay, instead of writing 1 CH3, I write 2 CH3. Okay, and then left with another CH3. So C9 already. C3, C4, okay, C4H9. Okay, so I have this plus. Okay, so this one is going to be, if I look over there, it's going to be a tertiary carbocation. So if I just put down the structural formula, so it will be C, then bracket CH3, 3, and then positive here. Okay, these are the possible 3 carbocations that you will get. Okay, you need to write down in structural form. Okay, and then benzene reacts with each of these carbocation, okay, in separate Friedel-Crafts alkylation reaction. So basically they are adding, do remember carbocation is a positive, they want negative. Okay, so they are positive. So all these carbocations, they are electrophile. Okay, they are electrophile. So they are going to actually undergo this Friedel-Crafts alkylation. So basically this positive over here, all these positive, they are going to join with the benzene directly. Okay, so if you look over here in the text, in the marking key, they have written in form of this skeletal formula. Why you must actually answer in form of skeletal formula? Because your first question, okay, they already mentioned in already given in this form. Okay, so since they have given in that form, you cannot just use any other forms like this page formula or something. So you need to try to follow the same. If you look over here, you can see that C, 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 C. So it means there's 4 carbon. So if I see 4 carbon here, so I can see 1, 2, 3, 4. So it means this is going to be the belongs to structure 1. When structure 1, the carbocation number 1, when they react with benzene, okay, so you are going to get straight away this over here. So I need to come up, okay, with the other 3, okay, but the only thing that I am provided with is going to be number of peaks in carbon 13, which is 8, 6, 7, and 8. how do I use this information, okay, to actually identify what type, okay, what type I'm going to get. Like for example, here you can see if this is done, okay, so we left with these three. So if I have, like for example, a benzene, okay, a benzene, when I react with this compound CH2 plus, okay, so maybe CH2 plus, okay, is bonded to one carbon. So this carbon is bonded to another carbon, okay, go down. And then this carbon is bonded to two other carbon, okay, this carbon bonded to two other carbon. So how do I show that it is bonded to our two other carbon? Maybe I show like this, okay. So I can actually show like that. Or if you want, you can actually also show in this way. Okay, this is another way. So this is going to be when it's bonded with carbocation number 2. Okay, now what I notice is I need to relate to this number of peaks. Okay, it means a different carbon environment. So if you look at the different carbon environment for this structure that is given over here, let's actually analyze. Okay, this is one carbon environment. This is another carbon environment, another different carbon environment, another different carbon environment. This is another different carbon environment. But I just want to ask Charlton, if this is one carbon environment 6, okay, how about this carbon environment, Charlton?
That also another environment.
Yeah, no, it's still 6. Why? I told you, in order to understand this, always think about symmetry. Okay, so this carbon is bonded to carbon number 5, but this carbon also bonded to carbon number 5, and the rest is all the same. You can see over there. So that is also 6. If this is 7, this is also 7. The same concept. Okay, so this is different, so it's going to be 8. So you can see 8. Can see, Charlton?
Yeah.
Okay, let me actually complete all this first, then we will actually put into there. So this is 2, yeah. So let's actually look at that is 2. So let's look at structure 3. Okay, if I have structure 3, I will have a benzene. This benzene is bonded to one carbon, and this carbon is connected to CH3. So maybe connected to CH3, and then connected to another 2 more carbons. So connected to one carbon, another carbon. So I'll have something like this. This is going to be structure 3. Now let's actually go to structure number 4. Okay, structure number 4. So if I have a benzene, and then I have the carbon, one carbon bonded to one carbon, and then I'm going to actually bond it to CH3, CH3, CH3. So 1, another 1, another 1, something like this. Okay, so this is going to be structure 4. Now what is important is to identify how many carbon environments so that I can actually put them where I want. Okay, so if you look over here, okay, when I wanted to put them, okay, into, hold on, yeah. Okay, when I wanted to actually put them, okay, into this different carbon environment, then I need to analyze first. Okay, let us actually analyze it properly. Okay, so I'll use a blue ink over here. Now, when I analyze for carbon number 2, okay, the structure 2, yeah. So how many possible carbon environment that I will have? Okay, please actually take note of this. This is 1. Okay, now is this carbon environment the same, Jody, or is different? This one, Jody?
The same way.
The same. Why? Because one is bonded to this, and this one is bonded to this, and the rest are all the same. So this is 1 also. Okay, this is also 1. This is going to be a different carbon environment, 2. This is going to be another different carbon environment, 3. This is 4. Now, after that, okay, the best way to look at it is by making it as a symmetry. Okay, if this is 5, Charlton, this is also
5.
yes. If this is 6, this is also 6, and this is going to be 7. So 7 carbon environment. So if I look at here, this is number 2, yeah. If I look at 7 carbon environment, this is going to be 7. So that is going to be the answer, the 7 carbon environment, which is going to be 2. So I draw this. Ken Charlton, this is done. Charlton, can you understand?
Yeah, yeah.
Okay, let's move on for this one. Okay, the one for 3. Okay, you see, this one is going to be, this carbon environment is 1. This is going to be a different carbon environment 2. This is going to be another different carbon environment. This is going to be another different carbon environment. Another different carbon environment. Make it a symmetry. This is going to be carbon number 6, 7, and 8. So structure number 3 will be for number peak of 8. So that's why you can see I written number 3 over there. And then the last one, okay, the one that reacts with carbocation number 4, okay, you see 1, but you see they are bonded with the same carbon. Carbon number 1 is bonded to this carbon. This is 2. Okay, this is 2. 1 is bonded to 2. This is also 1, bonded to 2. This is also 1, bonded to 2. This is going to be 3. Make it symmetry. 4, 4, 5, 5, 6. So there are total 6 different environment. So 6, this is going to be automatically this one. And then you draw the skeletal formula properly. Okay, this is my explanation on this. Okay, NMR, okay, number of peaks of carbon. So 4 marks. Okay, please take note. Okay, very important. Okay, if not, you will miss a lot of marks. Okay, let's actually move on. Number 6. But before that, okay, I'll stop for a while because this one is important. Any questions? Gabriela, Nicole, Victoria, Lavi?
No, sir.
Okay, Lavi, are you here? Yeah. Any question? No. Okay. Let's move on. Yeah. So here, number 6. Okay, compare and explain the relative acidities of chloropropanoic acid, 3-chloropropanoic acid, and propanoic acid. I think one of the common thing that when it comes to propanoic acid, 3 carbon. Okay, 3 carbon, then propanoic acid. Now, do remember this is automatically carbon number 1. So propanoic acid. If you have 2 chloropropanoic acid, if the chloro comes here, or if the chloro comes at 3, so the chloro comes over here, 3. Now, please take note, they want to talk about acidity, ability to donate the electron. Now, do remember Cl, okay, let me ask Arneta, Cl is electron withdrawing group or electron donating group? Electron withdrawing, she put in the chat. Yeah, so it is electron withdrawing. So do remember, in order to for this H plus to go out, okay, we know that oxygen is going to be electronegative. Okay, so this this electron over here, okay, they are going to actually pulled over here towards the oxygen. What happens? The bond between O and H is going to be weaker. Okay, so because of the bond is weaker, okay, the H can come out easily. But if you can actually make the H or the bond to be more weaker, what we can do is by adding the electron withdrawing group. Okay, so it depends on the position. If you add them closer, then the electron withdrawing ability will be more. If you're adding them further, then there is going to be less electron withdrawing effect. So in this case, if you just have propanoic acid without chlorine over there, then that's going to be, of course, it's going to be the least acidic. Okay, it's going to be least acidic. So the moment you actually put the Cl, okay, the moment you put the Cl, what we are going to have is going to be, you are going to have something like an electron being withdrawn. So if the electron is being withdrawn, so we are going to actually have something, a situation where the anything that has the Cl, okay, they are going to become more acidic. Okay, they are going to become more acidic. So the least acidic is going to be propanoic acid. So let's actually compare 2 chloropropanoic acid and 3 chloropropanoic acid. Very important. Carbon number 1, carbon number 2, carbon number 3. 2 is closer. Okay, if 2 is closer, better ability to withdraw the electron. So if 2 is going to be better ability, so this is going to be 2 chloropropanoic acid. And 3 chloropropanoic acid. Sorry, most acidic. Yes, 2 chloropropanoic acid is most acidic. 3 chloropropanoic acid is going to be somewhere in the middle. And then the least acidic is going to be the propanoic acid itself. Yeah. Now, explanation. Okay, please actually explain. We need to talk about the Cl. Okay, Cl, you need to mention about electronegative. Okay, they are electronegative. Because of that, okay, because of that, the OH bond will be weakened. Okay, OH bond is going to be weakened. And then you can also explain to compare these 2 and 3. Okay, the 2 is much more stronger because Cl atom is closer. So the OH bond is going to be more weakened. Okay, of course, they mentioned about stabilizing carboxylate anion more. Okay, but I think the most easier to understand is more towards the weakening the OH bond. Okay, so please actually focus on that. Okay, so any of these 2. Okay, so 1 mark you will get from this, a correct arrangement. Second is to talk about the Cl being electronegative. Okay, so they are going to withdraw the electron, so it will weaken the OH bond more. Okay, and then you need to compare 2 and 3. Okay, the one that is going to be closer, okay, will become better acidic. The one that is further is going to be not so good acidic because they are not going to weaken the OH bond properly. Okay, that's going to be the explanation. Now for this one, okay, of course, some of you would have actually seen this question many times. Okay, similar questions to this. It's very popular. Okay, they will give you 2 types of acid and then they will give you the Ka. Then they'll ask you, okay, they give you this mixture using this information, come up with the equilibrium constant. How to do that? The first thing that you need to do is to write down the equation. Like for this one is a methanoic acid, so write down, okay, this equation. This is going to be CH3CO is a carbonyl group with the ethanoic acid. So I just put, okay, I write down first. Now, if I want to write Ka, imagine this is K1 and this is K2, K1 and K2. So if I write down, okay, the expression will look like something like this. And the expression for K2 will look like that, okay. So if you have that expression, so let me see whether it's shown over there in the iPad. It's taking time to appear. Okay, let me. Okay, it's appearing over there. So you can see, okay, you need to actually use like K1 and K2. So if I want to actually write down the Ka value for this, so what I did was okay, let me screen share again. Hold on, yeah. Okay, just wait for a while. Okay, Aneta was asking, sir, do we say delocalize into or overlap? Both also the same. Okay, both also the same. So you can actually say the normally when we say overlap, Aneta, we normally say the overlap is actually related to orbitals overlap. Okay, so orbitals overlap. So whenever we are talking about lone pair of electrons, I think we normally say delocalized. So it depends on how you want to say. Okay, so let me share the screen. I hope it answers your question. So normally we will say delocalized into the pi system, the electrons. Now, if I write down, okay, the Ka, you can see this one, I take this one, I write down, okay, divided by this, I wrote down over here. So I need to actually use this information that I have, okay, and then I try to put in, like for example, I see I have CH3CO, CO2H here. So I can see it's a similar thing over here. And then here is there. So what I notice is, okay, for K2, no need to disturb, just put the K2. Okay, no need to disturb. But for K1, when I see for K1, I can see there's HCO2 minus, okay, at the bottom. But here, it is at the top. So it means that I need to flip this. Okay, I need to flip this. So when I flip, okay, I'm going to get the HCO2H on top, and then HCO2 minus at the bottom. So the H and H over here, when I do this thing, H and H will cancel. So eventually I'm going to get this. Okay, it means I came with this expression first. Okay, K2 divided by K1. That's actually the K equilibrium. Okay, so this is going to be the expression. Once I get that expression, so okay, so thank you. So delocalize into the pi or overlap with the ring. So basically this is Aneta, you say the lone pair of electron, they delocalize into the pi system. Okay, delocalize into the pi system. But if you want to mention overlap, you can say that the p orbital normally, when we want to explain related to overlap, the p orbital overlap, okay, with the overlap with the p orbitals in the benzene ring, okay, or something like that. They actually use the term overlap like this. So just see, but normally if you want to actually mention about delocalization, talk about lone pair, yeah. But if it is overlap, we talk about orbitals, okay. So maybe later when you try some questions, you can actually see that connection, yeah. So for this one, you just put in the value, okay. I know the K2 is going to be, just take the entire value, but K1 is 1 over K1, okay. So I just put over here 1.78. When I calculate, I get 22.9. So I just put 22.9 over there. Now, use your value in K equilibrium. You see your K equilibrium is going to be more than 1. If it is more than 1, it's going to be, the position is going to be more to the right. So it means we are going to compare, okay, 1 is actually, if it is more than 1, okay, then it's going to the right, okay. It means top, okay, divided by bottom. The top is actually more, it means more product. So that's why you want this. If you have less than 1, okay, then the equilibrium will be shifted to the left, okay, which is 0.9, 0.8, and so on. So for K1, can we say that it is a backward reaction? So the equation is flipped? Yes. Okay, yes, correct, Gabriela Nicole. So that is actually the what is going to happen. So it means that in order to achieve this equilibrium, okay, this equation, they are going to actually flip. Okay, they are going to go backward reaction. So it means, but to show this in this expression, I think better if you visualize this way using your maths. Okay, that is a better way to visualize. Okay, so you use this, then all the calculation will be cancelled. So that's why you actually have this. Okay, but anyway, it's 1 mark. Okay, now, so this one, okay, in this case, 22.9. Okay, 22.9 more than 1. Okay, therefore the equilibrium lies to the right. Okay, so you just need to mention that, okay, it's more than 1. If you don't mention it's more than 1, okay, you will not even get the 1 mark, even though this is correct. Okay, so please remember the explanation must be correct. The equilibrium constant, okay, the KEQ, okay, will be more than 1. Okay, you need to mention. Now, ethane diuric acid, this one we have discussed earlier. Yeah, so there is going to be 2 dissociation constant. It means that the H plus is being lost twice. Okay, so this one is going to be they are losing 1 H plus. You can see 1 H plus. Okay, then after that another H plus is lost. So do remember the first one, when they lose the H plus, is going to be easier, but the second one is going to be slightly difficult. So this is going to actually tell us why they have 2 dissociation constant. Okay, it means that if it is difficult, the H plus is less. Okay, if H plus is less, your pH, okay, or pKa will be lower. So you can see the pKa 1.23. Normally 1.23 is you just follow like pH. 1.23 is stronger acid, something like that. So it means that they have more H plus. Which one should have more H plus? This one should have more H plus, easier. Okay, so this one has less H plus, so it will follow the second one. So you can see pH pKa 1.23. I took the first one equation and I write it over here. 4.19, I took the second one and wrote it over here. This one we have discussed about this. Yeah, if you have a situation where the dissociation can happen 3 times, then you will have 3 pKa for that. Okay, so if let's say there's another CO2H, then you are going to have another pKa. So at the pKa, okay, the pKa will increase, okay, every single time when you remove. Yeah, or the Ka will decrease every single time you remove. Yeah, so do remember that. Now, state the mathematical relationship. This is very easy. pKa is negative log Ka. Okay, we have done this as well. Maybe I'll go very, very fast on this. Okay, you are going to have these 3 things. Okay, methanoic acid. Okay, this structure. So I've written this structure in this way. And then you have the ethane diuric acid, okay, over there. So they are asking you, okay, they have given you some observation. So which one will be suitable? So you can see methanoic acid has a positive reaction, the rest don't have. So do remember, okay, the positive reaction is happening, okay, because methanoic acid, if you want to oxidize, methanoic acid, you can even oxidize with any oxidizing agent. Okay, it's very, very easy to be oxidized. To be exact, here I written toluene, toluene and warm, and then I also put Phenol and warm. Okay, you can also use KMnO4 also. Okay, doesn't matter. Okay, doesn't matter. Okay, but KMnO4, what happens if you're using KMnO4? Ethane diuric acid is going to give you positive reaction. So KMnO4, no. Okay, cannot KMnO4. So only the toluene or Phenol. Okay, so the what is going to be our observed change? Okay. Okay, sorry guys. Okay, let me actually share the screen again. Okay, the connection is quite weak. Lavi, can you see my screen?
Yes, sir.
Okay.
Yes, sir.
I cannot hear you clearly also. Okay, but anyways, we're going to end. But let me actually finish this. Okay. So here, okay, can be oxidized. So you see, if you are using toluene, okay, if you are using toluene, you are going to get the silver mirror observation. If you are using Phenol, okay, Phenol, you are going to get brick red precipitate. So Phenol, okay, do remember we are using the copper 2+ ions, okay, in ammonia solution. So this one is ammonia, ammonia with excess ammonia silver solution as well, toluene. So please remember that. If you are going to use this one, okay, this is going to be basically to identify this structure, CH3C double. Sorry guys, I got disconnected. It's okay. Okay, I think we'll continue tomorrow. Okay. I'll just go very fast on that part and then we'll go on. Yeah. So is it okay, Shane? Can you hear me? So good morning, guys. Okay, so this one is optional. If you want to actually listen to my discussion today, you listen. Okay, if you want to continue with your revision on the paper 4.2, okay, on this 2020 May, you can also go ahead. If you have done that, okay, let me know. Okay, anyone who have done that, you still want some more revision from me, you let me know. I can actually tell you what to do. I can send you the papers. Okay, but today I will try to actually move on with the revision as well. Okay, we'll continue. So Justin, is it okay? Will you follow or you want to do other revision? Okay, I'm done with the other paper also. So do you want to follow or you want another paper? I can actually send it to you now if you want. Okay, I'll send you in the WhatsApp group. Okay, Justin, so I've sent you, okay, in the WhatsApp paper 4.1 together with the marking key. Okay, so if you want to actually continue there, I don't mind. Yeah, but today I'll just move on. Okay, let's actually continue the discussion. So you see here, okay, we have done this. I was mentioning about this Tollens region. Okay, Tollens region and Felling we can actually use to oxidize methanoic acid. So even Tollens region, a mild oxidizing agent, okay, they can actually oxidize, okay, methanoic acid. So in this case, okay, so Justin already done this paper also. So hold on, yeah, Justin. Let me send you paper 4.2 then. check this paper. Okay, if you have done, then let me know. I can actually send you another paper. Now, so you can see here, okay, tolerance region, okay, tolerance region, it will give you the silver mirror observed change for this, okay. Or if you're using Fairlink solution, it can be actually giving you the break rate precipitate, okay. But both of them, you need to warm them, okay. So Tolan, we use the silver solution in ammonia, okay. And Fairlink, we use copper 2 plus, okay. So it will be copper 2 plus changing into copper plus, okay. That copper plus copper oxide, okay, is going to be the brick rate precipitate that is going to be formed, okay. Then for this second substance that is actually tested positive, okay, this one is going to be testing for CH3 C double bond O, okay. So this one we can actually use triiodomethane reaction or iodoform, okay. So you use alkaline aqueous I2, okay. So it will give you yellow precipitate if positive, okay. So or you can actually use 2,4-DNPH. 2,4-DNPH is to test for carbonyl compound, okay, or to anything that has C double bond O. Okay, in this case, it's possible also to test, okay, using the 2,4-DNPH. It will give you orange precipitate. Okay, the others, okay, they do not actually, they are not carbonyl compounds, okay, especially you see ethanoic acid, okay, ethanoic acid, okay, because they are carboxylic acid, okay, they do not actually give you positive results with DNPH, but this one, the carboxylic acid is over here. So they test this part, okay, so it's possible, yeah, possible to get positive reaction. And then the last one, they say both of methanoic acid and ethane dioic acid can be oxidized, so it has a positive reaction. So in this case, okay, this one is going to be, both of them can be oxidized only by a strong oxidizing agent, so it's going to be acidified potassium manganate. And then the decolorized, it means the purple color will be decolorized, okay. So this is going to be the observation. So you need to actually, we have done this before also, okay. So please revise on this. So the next one is going to be a sample of pyruvic acid, okay. It's going to be analyzed, okay, by using the carbon-13 NMR spectroscopy. And then they have identified 3 peaks over here. So we need to actually find out, okay, by circling the carbon atoms, because they are using carbon-13 NMR. So by circling the carbon atom responsible for the chemical shift, stating the hybridization. So I think once you know which carbon, I think the hybridization is quite simple. Okay, so in this case, okay, we are going to actually just identify, okay, which one. Like for example, if chemical shift, so let me actually show you the, I share the screen, yeah. Hold on, let me actually just go here directly. Data booklet. This is the information that we are going to use. Okay, let me take a screenshot. And then hold on, yeah. Okay, I'll put it here. Okay, this is the one that I took, okay, from the data booklet. So you can see here, okay, I have the chemical shift at 27. So I need to look for 27. And then they said that, okay, the carbon atom responsible. So we need to actually look for either the carbon atom, there are 3 carbon atoms, okay. One is actually carbon atoms attached to 3 hydrogen. we have another carbon atom which is going to be attached to oxygen, or another carbon atom that is attached to oxygen and OH. Okay, so these are the three carbon atoms. So if you look over here, okay, if you have CH3, okay, the only thing that come over here, this one, CH3. So if you have CH3, then it's going to be 0 to 50, okay, chemical shift range. 0 to 50, so most probably this one, okay, 27. So it's going to be this carbon, so I select. Okay, and then I have, okay, let's say this one done. Okay, C double bond O. Okay, let's look for C double bond O. So if I look for C double bond O, then it can be either next to carbonyl or carboxyl group. Okay, next to carbonyl or carboxyl group, or it can be also, okay, it can be just directly a carboxyl group. Okay, let me see here, which is going to be the C attached to carboxylic acid group. Yeah, you can see carboxylic acid group. So there are two over here. This one is going to be C double bond. This one is ketone. This is going to be aldehyde. So we are not going to talk about ketone and aldehyde. Maybe this one, yes, C double bond O. Okay, let's actually see C double bond O. So possible, this one also, this one, definitely nothing to do with this. Okay, next to oxygen, this is going to be next to oxygen directly, carbon next to alcohol. There is no alcohol, no direct oxygen, so no. This one, okay, so basically I'm looking at the C double bond O and then R, C next to carbonyl. So let's actually see. So here, okay, if you're looking at the number 163 and 192, so I'm not referring to these numbers. So I'll just put, okay, I'm not referring to all these numbers. So I have eliminated, okay, most of it, okay, 163 to 192. So maybe here, okay. So the rest is not there. So it means only here we have identified. So here, okay, you can see the one that is going to be 163 must be the one that has carboxyl group, which is going to be carboxylic acid. So I can say that the one that is going to be carboxylic acid, this carbon. And then the 192 is going to be the normal aldehyde or ketone. Okay, so it's going to be aldehyde or ketone, this one. So I circle that. After that, I think quite easy. If you want, you can refer to hybridization, but I think by now you should be pro at this. Okay, why? Because by just looking at the structure, you should be telling us what kind of hybridization is this. Okay, like for example, you have carbon 1, 2, 3, 4. There's 4 orbitals, okay, for that carbon. So it must be sp3 hybridization. Okay, and then if you look over here, 163. So 1, 2, only take one of the double bond. Okay, so it's going to be 3 orbitals. So it's going to be sp2 hybridization. And then if you look over here, so 1, 2, take only one from the double bond. So this is also going to be sp2 hybridization. Okay, so you identify from there. So this one is quite easy. Okay, quite easy. You need to actually just list down, okay, what kind of carbon environment that you have, only 3, and then it's easier to identify. Okay, so next question. Okay, an ester of pyruvic acid, okay, dissolved in CdCl3 and analyzed by proton NMR spectroscopy. Okay, CdCl3 and then proton NMR spectroscopy. So you know CdCl3 is going to be, we are talking about something whenever you have more peak over here. Okay, this is going to be something related to your high resolution. Okay, high resolution NMR spectroscopy. So you can see that, okay, there are splitting pattern. Okay, there are splitting pattern. So how to actually analyze this? Okay, the important thing that you can actually see here. Okay, if I just put them together here. Okay, I want to actually look into the hydrogen environment. okay, the hydrogen environment. So it means the hydrogen over here, okay, the hydrogen over here, okay, and the hydrogen over here. Okay, these are the environment. That's why, okay, you can see that they only have 3 peaks over here. Okay, 1, 2, 3. Now, out of these 3 peaks, okay, you need to know that the splitting pattern that happens, okay, it involves the carbon that is attached to the carbon. Like for example, if let's say this carbon, okay, this carbon, the hydrogen is attached to this carbon, but the next carbon, okay, if they have hydrogen, okay, then this hydrogen spectrum will have splitting, so it will actually be affected. So in this case, if I just look at this CH3, okay, for this hydrogen over here, if I look at the neighboring carbon, there is no hydrogen. Okay, if there is no hydrogen, there will be a single peak. Okay, you can see that they have a single peak without splitting. Okay, so this peak, okay, automatically represents over here. Okay, I want you to actually understand this. Okay, and then you have this environment, okay, H2, okay, that hydrogen. And if you look at that environment, the carbon that is attached next to that, okay, is going to be this carbon. Here, there's no carbon, so no need to worry. Okay, this carbon has 3 hydrogen. Okay, so Charlton, if there is a splitting, okay, for this CH2, which is the hydrogen over here, how many splits will you have?
For which one?
For this hydrogen?
3.
No, you must look at the carbon
Okay.
next to
4,
it.
4.
So 3 plus 1, yeah? 3 plus 1, which is 4. So you need to look at 4. So this one has 4 splitting. So the one responsible for this proton will be this one. Okay, and then the last one, you can see this hydrogen environment. The carbon next to it is going to be 2 hydrogen. So it means 2 plus 1, 3. So you can see that they have 3. I hope you understand this. Okay, this is very, very important. Okay, Victoria can. Now, use the proton NMR spectrum to complete the table. Okay, group responsible for the peak. Okay, 1.3, 2.2, 4. Okay, group responsible for the peak. You can see we have already identified. Okay, so the group responsible for the, yeah.
For the CH2, why is it 4 peaks?
The CH2, okay, because we are
Yeah.
looking at this carbon hydrogen environment is proton, right? So this environment, okay, is going to be affected by the neighboring carbon. So you need to look at the neighbor. Okay, this is, let's say this is your house, and then you have to look at your neighbor. Your neighbor is this one. Your neighbor has 3 hydrogen. So if your neighbor has 3 hydrogen, so n plus 1. So 3 plus 1 is 4. So for this one must be 4. It means 4 splitting. 1, 2, 3, 4. Is that clear?
For the CH3, only 3.
For the CH3, you see, okay, if I put this is your house, you need to look at the neighbor. The neighbor is going to be the carbon next to it. So this is the neighbor. So the neighbor has 2 hydrogen. So if the neighbor has 2 hydrogen, then n plus 1, 2 plus 1 is going to be 3. So that's why for this one, we'll have 3 splitting. Ken, who's
Okay,
this?
thank you, sir.
Is it Shane or what?
Shane.
Okay, so please take note of this. Okay, because one of the common mistake that students will do, okay, they think this is CH3, they go and add 1 and then say that this CH3 belongs to this, which is wrong. Okay, you will lose automatically 2 marks from here. Okay, which is totally wrong. Okay, so for 4, it's supposed to be for the C attached to 2H. So the group responsible for the peak is going to be C attached to 2H, 2 H, 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 the hydrogen attached to, let me actually see how to represent the answer here. Okay, hold on. How to represent the answer. Okay, they say the environment of the carbon atom. So they say alkane. Okay, they say alkane, or you just put CH3 like what I did just now is okay. So like for example, okay, if it is going to be 1.3, this is 1.3. So it's going to be CH3. So group responsible CH3. And then if it is going to be 2.2, so they say that, okay, 2.2 is this one. So this one is going to be CH3. Okay, so CH3CO, they say CH3CO. It means this group. Okay, or they say CH next to CO. Okay, CH next to CO. Up to you how you want to represent your answer. Yeah, or if you already show the arrow, also it's going to be one of the way to for the examiner to identify. Yeah, so for 4, okay, it's going to be the CH2, okay, attached to next to O. Okay, so how to actually represent? So it's going to be CH2O, or the CH, okay, the CH next to the CO. Okay, up to you how you want to represent, but you can see, okay, basically this one for this, okay, this one for that, this one for this. Okay, already identified. Now, number of hydrogen atoms responsible for the peak, that this is another thing which is important. The hydrogen, it means how many environment. Okay, it means having the same environment. So if you look at the 1.3, okay, so this is 1.3. How many environment representing over here? How many hydrogen? You can see CH3. So let me erase this. You can see that this is going to be CH3. So there are total of 3H1. Okay, so I put over there. And then if it is going to be singlet, okay, for 2.2, okay, the one that has CH3O, this one, okay, so this hydrogen, okay, so total they have 3 also, so you put 3. And then CH2O, which is going to be this one, okay, how many? Total 2, so 2. Okay, so the next one, okay, which is going to be, okay, that I want to discuss is this one. They mentioned that deuterium, okay, oxide, okay, which is going to be water basically, okay, which is going to be, we call it heavy water, okay, because the isotope, okay, of hydrogen that is being used is going to be 2, okay, so it can be used as a solvent in proton NMR spectroscopy. We have learned about this. When you use heavy water, what happens is, okay, the peak that is attached to nitrogen to hydrogen, or the O to hydrogen, okay, this is going to disappear, okay, disappear. So the proton NMR spectrum of alanine in CdCl3, which is the normal one, has 4 peaks. The proton NMR spectrum of alanine in D2O has 2 peaks. So 2 peaks when disappearing. So in this case, on the diagram of alanine, circle the proton that shows peaks in both NMR spectra. So it means that the one that is gone will be this attached to nitrogen, attached to the OH. So this one will be gone. So I just put gone. So we need to circle the proton that shows peak in both NMR spectra. So it means that the one that I need to circle is not these two. Okay, it must be the one that I circle in red is going to be the proton that shows peaks in both NMR. So it's going to be this one and this one. Okay, that will be the answer. Or you want to actually circle together, also can. Okay, please actually do that. Now, on the diagram circle, explain your answer. Okay, why only 2 peaks? Why this one is gone? So you need to explain about the proton exchange. Okay, so here why it stays. Okay, so you just need to explain the above 2 proton, the above 2 protons or the above circled, the circled protons do not get exchanged with D2O. Okay, that will be the answer. So the ionic product, okay, of D2O, which is similar to water, yeah. So if I have H2O, okay, it's supposed to give me H plus and OH minus. So now if you have D2O, it's supposed to be D plus plus OD minus. Okay, so same thing. So they say that the Kw, okay, the Kw for water is 1 times 10 negative 14, but this one is 1.35 times 10 negative 15. So they say write the expression of Kw, which is the same. Okay, you just need to use this. So the expression is going to be OD minus and then D plus. That's it. Divided by water, no need because it's constant. Okay, so we no need. It's similar like Kw equals to H plus and then OH minus. It's the same. Okay, this is the answer. Now calculate the pH, okay, of the pure D2O. Assume, okay, this is going to be equivalent. So basically, if you use the normal formula, if it is going to be like this, we say Kw equals to this to like normally we use Kw equals to H plus and OH minus, and we know that this H plus and the OH minus, they are the same. So what we do is H plus, then we say another H plus because this is going to be the same. So you are going to have H plus to the power of 2, then you can calculate the pH. But in this case, you just do the same thing. Okay, so you have OH minus and D plus. The OH minus is the same as D plus, similar like this. So you are going to get D plus to the power of 2 is 1.35 times 10 negative 15. Where do I get that? They already give you this. Okay, so you just need to have D plus, which is going to be square root of 1.35 times 10 negative 15. Once you get that, okay, you can find out what is the concentration of D plus is 3.67 times 10 negative 8. You want pH. So pH is going to be, you can calculate negative log, and then you put 3.67 times 10 negative 8. You will get 7.43 as your answer. Quite simple. Yeah, quite simple. This one is just basically related to this Kw equals to H plus times OH minus. Okay, they didn't ask you difficult question over here. Okay, total, have a look, 23 marks. Okay, solid. Okay, from where? Okay, all these things combined, you see. That's why organic chemistry, very, very important. Yeah, please take note of that. Okay, so and then chemical analysis, you can see how many marks is given for this question. So you see chemical analysis, I think related to chemical shift, 2 marks. Okay, and then this one, they give you another 3 marks. So total 5 marks. Or if you want to include this, then it's going to be total 7 marks. So sometimes they give you more. Yeah. So this one, please take note. Okay, the next question, okay, you have silver carbonate, okay, Ag2CO3 sparingly soluble in water. So normally when you have that, okay, we normally write the equation Ag2CO3 solid, they give you 2 Ag plus and CO3 2 minus, aqueous aqueous. So here they say the solubility product KSP is going to be 6.3, okay, times 10 negative 12. Okay, write an expression so and state its unit. Yeah, so write the expression, just use this one, Ag plus to the power of 2, CO3 2 minus. Okay, this is going to be the expression. This one, please check. Okay, I think the answer key is wrong. Okay, because when they say state its unit, okay, you can see it's going to be mole, okay, dm negative 3. So to the power of 2 times another mole dm negative 3, you are going to get mole to the power of 3 dm negative 9. Okay, I think in the answer key is slightly different. Okay, so maybe let me check whether, yeah, no, answer key is correct. Okay, but I think one of the answer key last time when I checked, it was actually wrong. Yeah, So the previous one. So this one is actually following the answer key. So let's actually move on. Okay, when I move on, okay, you can see that calculate the equilibrium concentration, okay, of Ag plus in saturated solution. So I want to find what is going to be the equilibrium concentration. So if you look at the, let's say the equation, like for example, if you have, okay, a particular let's say a solubility, okay, like for example, we use the solubility as X. So we know that this is 1 mole, this is 2 moles, and this is 1 mole. So we know that, okay, when you look at the solubility, imagine it's X. So we know that this one, okay, every 1 mole will give you 2 moles. So if this is X, so this one will be 2X, 2 times X. And then this is going to be 1, so it's going to be X. Okay, that is going to be by using the term solubility. But they want the concentration of Ag plus. Yeah, be very careful. Later, once you actually find the X, you want Ag plus. So Ag plus is 2X. Some of the students forget to times by 2. Okay, so please take note. Okay, in this case, if I use the KSP, what I can use is going to be 6.3 times 10 negative 12. You can see 2x to the power of 2. So 2x to the power of 2. And then I put x. Okay, just put in the KSP over there. Then I will get the 4x to the power of 3. I can find out what is x. Okay, I found out that the x is like this. Okay, but this is not the answer that I want because they want the Ag plus. Ag plus is 2x. So times by 2. This value times by 2, you will get this answer. So one of the common mistake is students forget to times by 2. They just give the x value. Okay, this is very important. Now, next question. Solid, okay, silver carbonate is stirred at 25 degrees Celsius, okay, with this amount of silver nitrate until no more Ag silver carbonate dissolve. So it means now most of the, okay, the assumption, there is an assumption. It means that silver carbonate is sparingly soluble. So when you put silver nitrate is totally soluble. They will contribute most of the silver ions over there. So here, okay, the assumption is all the silver ions coming from silver nitrate. So we are actually ignoring the fact that, okay, silver carbonate gives you Ag plus. Okay, we ignore that fact because most of it is going to come from here. So if I use the formula KSP, okay, you can see this is KSP. Now, okay, the most of it, okay, the most of the concentration of Ag plus, okay, because we are going to still use this formula. Ag plus is coming from, okay, the silver nitrate, and you can see, okay, if I use 0.050 mole per dm cube, okay, I am going to get, okay, I'm going to get this amount, this concentration of silver ions. Okay, it's because why? Silver nitrate gives you Ag plus and NO3 minus. So if you have this 0.05, you will get 0.05 as well, okay, in terms of mole. So I put over there. Okay, and then for carbonate, I'm not sure because it's sparingly soluble. I'll just put it over there. And now, okay, I want to find out what is going to be the concentration of carbonate ion in this solution. So you just use the formula, okay, to the power of 2, don't forget. Okay, you will get 2.52 times 2.52 times 10 to the power of negative 9. Okay, that's going to be the concentration of carbonate. Now, this is very, very important. Okay, an electrochemical cell is set up to measure the electrode potential. Okay, for Ag plus and Ag half cell using silver carbonate. Okay, so you are using silver carbonate. So it means you are going to measure, okay, with the standard hydrogen electrode. If they want, they can actually ask you to draw the diagram. But since they already asked you to draw diagram, they no need to actually ask you again. Okay, but if they want for this question also, they can ask you to draw diagram. But what you need to take note is we are using saturated Ag2CO3. Okay. using the data booklet, okay, your answer to A2 and the Nernst equation to calculate the electrode potential, okay, for this. Now we use the Nernst equation, okay, when we are dealing with the E value involving the concentration that is not under standard condition. It means when the concentration is different than 1 mole per dm cube, we can still measure the E value, okay, and then how to do that? You need to use the formula. Now, the formula that we have learned last time, you can actually have a look at your notes, okay? My PowerPoint, okay, E value is going to be this one, okay, plus R is going to be gas constant times temperature in Kelvin, okay? This one, Z is going to be number of moles of electrons, okay? And then Faraday, okay, 96500. And then ln oxidized version divided by reduced version. But we know that, okay, all this, okay, can be constant. Why? The temperature is going to be 298 Kelvin, okay, 8.31, and then Faraday is constant. So what they did is to simplify. Okay, they managed to simplify the formula. So you come with this formula. If you want to memorize, then you memorize this formula. E value is the E standard, okay, at the normal condition. Okay, 1 mole per dm cube. It can be obtained from the data booklet. Plus, okay, they have times all these constant, you get 0.059. This is going to be depending on how many number of electrons that are there. And we are no longer going to be using ln, it's going to be log and then oxidized, no reduced version, oxidized. Okay, so the one that is oxidized is going to be the positive ion, which is in this case Ag plus, concentration of Ag plus. So here I want to use this equation over there. So if you want to calculate the E value that I want to calculate, is going to be E cell, which is 0.8. This one you look in your data booklet, you will notice that the Ag plus, okay, electron to give you Ag, the E value they have given is going to be 0.8 volt. It's given, okay, it's given from the data booklet. So I put 0.8. And then put the value plus, okay, do remember this is involving 1 mole of electron. So this is going to be 1, 0.059, I just put log, okay, and then the oxidized version. The oxidized version is Ag plus. And Ag plus, do remember the oxidized version of Ag plus, it means rather than looking at the Ag plus, okay, we just look at the silver carbonate. Okay, silver carbonate, if you look at the silver carbonate earlier, okay, you see that the concentration of Ag plus is 2x. Okay, the concentration is going to be 2x. Or when you calculate the concentration of Ag plus, I times by 2. Okay, I times by 2. But in this case, we are talking about, okay, we are talking about silver carbonate. Okay, silver carbonate, which is in this case, we are not going to use the 2x. We are going to use, okay, because why? 2 to 1. Okay, we are going to use the concentration of what? We are not going to use the concentration of silver ions, okay, because it's actually sparingly soluble. So we are going to use the concentration of Ag2CO3. So if this one is going to be the value, which is 2.33 times 10 negative 4, I am not going to select this. I'm going to select 1, okay, ratio, which is 1, which is going to be half of the 2.33 times 10 negative 4, which is, okay, 1.1635. This is very important because students will ask questions on this. Okay, you see this one, I put no problem, log. What do we use over here? Do we use, okay, silver ions, which is 2.33 times 10 negative 4, or this one? But in this case, to answer that question, you need to use, okay, the one over here, because silver carbonate, okay, they are sparingly soluble. So the concentration of silver carbonate is used rather than concentration of Ag plus. Okay, so it's going to be half of it, which is going to be this value. Okay, so I just put that value 1.1635 times 10 negative 4. Then now you calculate the E value. Okay, if you calculate that E value, you will get how many volt. Okay, you are going to get, okay, let me check. You are going to get 0.57 volt. 0.57 volt. Okay, so this is going to be, but please remember one of the common things that we actually do is going to be voltage. Okay, voltage is going to be always positive. Okay, so no need to actually put plus. Okay, but whenever it comes to entropy, whenever it comes to your energy, whenever it comes to, let's say, enthalpy, okay, please include plus or negative. For voltage, no problem. Okay, in this case, it's understood. But if you still want to give, yeah, please go ahead. Okay, so this one is going to be plus 0.57. Okay, so different than the voltage that we expected, which is supposed to be, okay, 0.8. Okay, it's supposed to be 0.8. Now, because we are using different concentration of Ag2CO3, okay, so now it became 0.57, less than 0.8. Okay, let's continue. Now, this is going to be question about entropy. Now, silver chloride is sparingly soluble in water. So yeah, you can see solid, aqueous, aqueous. The equation is given. So here they say enthalpy of solution. Now, one thing that you need to remember when it comes to enthalpy of solution, okay, if the solution is going to be positive, so it's non-soluble. If the enthalpy of solution is going to be negative, then it's automatically soluble. Okay, this is very important. Now, the standard entropies are shown. Okay, calculate the standard entropy of solution. So it means the standard entropy of this. So if I want to do that, it's quite simple. Okay, you just if you revise back, okay, about the formulas involved for this. Okay, the formulas are entropy of the system equals to the product minus entropy of the product minus the entropy of the reactant. Entropy of the surrounding is going to be negative delta H divided by T. S total is entropy of the system. This system, you plus with this surrounding, you are going to get S total, entropy of total. If you substitute the formula, you are going to get something like this, where you are going to get Gibbs free energy is going to be, you can actually represent, okay, using Gibbs free energy. Gibbs free energy is going to be negative T, then it means this entire formula, if I times by negative T, I'm going to actually get this equation. So this one, if you try to remember, I think last time I told you to remember Mr. Gopi is not so hot. So it's not so hot. Okay, so you just put over there. Okay, so this one, I do not know whether you can actually remember this and so on, but you need to actually know about this formula. Okay, so what do I know about entropy and Gibbs free energy? Okay, your entropy, if your S total is positive, which is more than 0, okay, then the reaction is spontaneous. Okay, but since the Gibbs free energy is going to be negative T, okay, negative T times the entropy of the total, this is going to be different. Like Gibbs free energy, if the Gibbs free energy is less than 0, okay, then if Gibbs free energy is negative, then it's spontaneous. So this is going, then vice versa. Okay, vice versa. So in this case, with the aid of calculation, explain, okay, before that, I think we just do this. Calculate the standard entropy change of the solution. So in this case, they want the entropy of the system. Okay, the S product minus the entropy of reactant. So you can see this is going to be reactant. This is the product. So the reactant, okay, you can see the reactant is 96.2. Okay, so then the product, okay, is going to be this. Okay, so product minus the reactant. So product is 72.7 plus 56.6 minus the reactant. You are going to get positive 33. Okay, this is going to be positive 33, but do remember it's in joule. okay, but this one was in kilojoule, okay. So this one is in joule, okay, please remember this. Explain with the aid of calculation why silver chloride is insoluble. Now, if you want to actually show silver chloride is insoluble, then the entropy change of solution is not enough, okay. What you need to do is going to be, you need to include the S total, or you can actually calculate the Gibbs free energy. If you can show that any of this, okay, and then say that it's non-spontaneous, then it's actually the answer. So you can see, like for example, I use the Gibbs free energy, okay, I use the formula, okay, you know the enthalpy change, they already give you 65.5, but since it's in joule, this one I need to change, okay, from kilojoule to become joule. Okay, one of the mistake that students always do, they forget to change. Then minus T, do remember the T that they have given you is going to be 25. So 25 plus 273, 298. Okay. And then the entropy, okay, of the system is going to be 33, or the entropy of the solution here. So I put over there, then I calculate, and I will notice I will get, okay, I think this one is the answer for this. So this one plus 55,666. Okay, so this one, since I'm getting a positive Gibbs free energy, okay, since it's positive, then the reaction is going to be non-spontaneous, okay, because if Gibbs free energy is negative, then only it's spontaneous. Okay, you can use this formula, or you can always use the S total. If you can calculate the S total and you show that the S total is negative, okay, then it's already also an indication, okay, that this reaction, this silver chloride is insoluble in water. Okay, so before I move on, is there any question? Let me actually check first. Okay, Gabriela, Nicole, any question?
No, sir.
Okay, let's move on. Yeah, so explain what is meant by the term buffer solution. Okay, buffer solution we have discussed. I think even the previous paper that we done, they actually asked the same thing. Okay, the 2020, in the same year. Okay, you can see in the same year, the one that this paper is May paper. Okay, the one that we did was March. Okay, so this one is going to be, they're asking about the same thing, buffer solution. So a solution that can resist the change of pH when a small amount of acid or alkali is being added to it. So that is going to be the definition. A solution that resists changes in pH when small amount of acid and alkali added. So you get 2 marks. Now write an expression for the acid dissociation constant for ammonium ions. Okay, so ammonium ions, okay, to give you ammonia and then H plus. So expression Ka is going to be H plus, okay, and then ammonia, and then divided by ammonium. Okay, so this is going to be the expression. So now write 2 equations to describe how a solution containing ammonium ions and ammonia can act as buffer. So basically, if you have this ammonium ion, okay, and then NH3, if I add H plus, or if I add OH minus, what will happen? Okay, so if I just simply add H plus, okay, the ammonia will react with the H plus to give you NH4. Okay, so you can actually write down ammonia plus H4, H plus to give you ammonium. Okay, but in the marking key, they, instead of giving this, I think they give you ammonia when they act in form of H3O plus, which is the same H plus. Okay, they are going to give you ammonium ion plus OH minus, which is ammonium ion and then water. Okay, so this one is up to you which one you want to use, as long ammonia is reacting. And then for hydroxide, when you add, so it's going to be an ammonium, okay, plus the OH minus. So they are going to give you ammonia plus water. Okay, this is going to be the reaction that's happening. So maybe the question will be, okay, Mr. Gopi, why cannot use this one? Yeah, it's still correct. Okay, then 2 questions over there. Now 2 equations, okay, that they want. Now, the numerical value of Ka, this is very interesting as well. Okay, the numerical value of Ka is given. A buffer solution was prepared, okay, using ammonia, okay, and excess hydrochloric acid. So we need to calculate the pH of buffer. Now, in order to calculate the pH of buffer, okay, what we need to do is going to be by using this formula. Okay, please remember this formula. pH equals to pKa plus log salt divided by acid. But in this question, I will not suggest you to use this, okay, because if you use that, okay, if you use that, this is salt divided by acid, but the ammonia, this is not acid, okay, this is not acid. So if you use this formula blindly, you will get a different answer. Okay, so I'll teach you how to use. Okay, basically what I need to do is find out first, okay, what is the number of moles of ammonia and what is the number of moles of hydrochloric acid. Because if you use the formula, what's going to happen is ammonia will react with HCl, okay, to give you ammonium chloride. So they have mentioned ammonia is in excess. Okay, so when I calculate, okay, when I calculate 0.2, okay, times 0.2 divided by no need to divide by 1000, is dm already. 0.2 times 0.2, you are going to get 0.04 moles. And then for ammonia, okay, when I do times that, okay, I am going to get 0.2 moles. And we know that this is going to be in excess, so it means that the limiting region is HCl. So 0.04, okay, and then to give you 0.04, it means 1 mole to give you 1 mole. So because of that, okay, because of that, you are going to have a certain amount of ammonia that is going to be reacted, which is 0.04 reacted. So what is left? Okay, what is left? Okay, ammonia that is left over here is 0.2 minus 0.04, which is 0.16. Okay, so if you look at the concentration wise, okay, you can see 0.80 dm cube, 0.20 dm cube. So total is 1 dm cube. So this is going to be number of moles. Okay, so if you want to find the concentration, number of moles divided by volume. So 0.16 divided by 1. Okay, very important because in this case, it just happened to be 1. What happens if they give you different dm cube? Okay, so you need to still divide. Okay, in this case, they don't want to actually burden you with that. They just give you an easy question. So they ask you, okay, to calculate the pH of the buffer solution. Now the pH, okay, is supposed to be we use this one, but I will not suggest you to use this because why? Okay, if you use this formula, okay, I will teach you how to use the formula. But again, we are talking about ammonium. Okay, Ka for ammonium is given. So the Ka of ammonium is given. It means you need to write down the ammonium ions equation. Ammonium to give you ammonia plus H plus. So if I write Ka, the value that's given to us, 5.6 times 10 to the power negative 10, it's supposed to be written in this form. Okay, it's supposed to be written in this form. So what I know over here is the number of moles. Okay, if I want to calculate, okay, the number of moles of ammonia, this one I think we already calculated earlier. Okay, the H plus. Okay, if you want to find the H plus, I think straight away here. Yeah, this one is just now. Okay, so if I want to find the H plus using this equation, it's simple. The concentration of ammonium times with this divided by the concentration of ammonia, which we have already here. Okay, so what I did was, okay, 5.6 times 10 negative 10 times with ammonium, okay, times with 0.04 divided by ammonia. Okay, this is ammonia 0.16. Once you get that, you will have concentration of H plus. Okay, once you have concentration of H plus, okay, that's going to be you can calculate what is your pH by using negative log of your answer, and your value you are going to get 9.85. Okay, 9.85, which is going to be your pH. Now if I really want to actually use this formula, okay, then what should I take note? you take note, this is salt divided by acid. I remember salt divided by acid. Okay, in this case we are not talking about, okay, the salt in this case is going to be supposed to be the ammonia. Okay, normally if you have ACl, okay, if it is acid, then it will be H plus and Cl minus. Okay, the salt is Cl minus divided by the acid. Okay, but here, okay, if you look at this, okay, so this one divided by this one. So if you look over here, if you follow the formula, okay, if it is, this is Ka, so it's supposed to be you take, okay, the ammonia, okay, the ammonia divided by ammonium. It's supposed to be in that way. So it means that, okay, the ammonia is 0.16, okay, divided by 0.04, okay. So that's supposed to be the way to calculate rather than using this way. Okay, if you use this way, then it's wrong. Okay, I'm just giving you some example. Okay, so if you want to calculate, do not straight away use, okay, the salt. Okay, which one is a salt? Or I take this one 0.04. Okay, and then this is acid, so I take this one. No, it's not like that. So you take you calculate yourself. Okay, you will notice that you are going to get two different answers. So the one that we are looking for is 9.85, and the best way to do this is not by using this formula. Okay, the best way is straight away by using the Ka. Okay, use the Ka straight. If you want to use the formula, yeah, please be very certain. We are talking about salt, okay, divided by acid. So in this case, you need to be very careful what to select. Okay, hold on, guys. Now, the next part, yeah, let's actually move on. Any question up to here? Gabriela, Nicole, can you actually understand why I said this one need to be careful?
Yeah.
Okay, be very careful, because if you don't do that, you will get a different answer. Okay, you will get a different answer. So the best way is to use this method. Okay, try to avoid the formula as much as possible. Okay, try, but I think if you want to memorize the formula, yeah, this one you memorize. Okay, this one, okay, memorize easier. Okay, these are the things that you memorize. Okay, next question. Okay, manganese 4 oxide catalyze, okay, the decomposition. Okay, anyway, it's already 12:30. If I do this, okay, can we just finish this? Okay, so that we don't end up, okay, let me actually go very fast. Yeah, so you have this I don't think so we can go fast for this. Okay, this one maybe next class. Okay, this one, okay, finding the equation rate. Okay, if you have the rate, okay, they say rate constant is there, initial rate they want to calculate, so you found out that this is going to be first order, so just put in, and then you can calculate by putting the K in, calculate this, you can actually calculate this. Okay, this one no problem. Okay, I'll just show you this one. Okay, a 4-step mechanism is involved. They say step 1 is a rate determining step. Rate determining step is the slowest step. Now, what do you need to remember about the slowest step? Okay, whatever value that comes here is also going to tell you that that is going to be the number when you write the rate equation. Okay, please remember that. One thing that we learned last time. And then whatever that appeared in the reactant in the slowest step must also appear in the rate equation. If not, cannot. Okay, so you can see H2O2 and I minus must appear in the rate equation. So in this case, they say that use, okay, state what is rate determining step. So it's a slow step, yeah, so quite easy. Use this mechanism to construct a balanced equation for this reaction. So when you write the balance equation, I know must appear in the equation. Okay, must appear in the equation. So this is intermediate. If I combine step 1 and step 2, okay, intermediate, it can cancel. Then when I combine all these steps, I can also cancel this and this. Okay, when I combine step 3 and step 4, I will have this. So basically, when I join all of them together, what I get is going to be, I'm going to get H2O2, I plus I, so I 2I minus, okay, H plus, 2H plus. All those cancel, will not be there. So H2O, H2O, 2H2O, and I2. And you can see that, okay, you can see the slower step, they have H2O2, they have I minus, okay, but they have H plus over there. But H plus is not going to be in the rate determine. It's not in the rate slow step, okay, or slower step. So it can be in the equation, okay, but they are zero order, okay, they are zero order. So use this mechanism to construct equation, done, okay. Deduce the order of the reaction with respect of the following. Okay, so deduce the order of the reaction. You deduce not from the equation. Please remember that. Do not, okay, this one is only for this. Okay, only for that. But when you deduce the order, you refer back to here. Okay, so when you have H2O2, there's only one. So 1. I minus, that's 1. Only 1. H plus didn't exist in slow step, automatically 0. I want you to remember this. Okay, very, very important. Okay, the rest I think quite easy. You can actually just you see possible oxidation state, everything is there. I think to answer this question for BEM, okay, why, okay, transition elements have a variable oxidation state. Okay, the reason is quite simple. If you don't understand the marking key, they say that the 4s and 3d subshell, the energy is similar. Okay, that's why they have multiple oxidation state. But to explain that, okay, maybe if you look at sodium or magnesium, okay, Mg2 plus, you see if it is group 2, if I look at the ionization energy, if I remove one electron, then when I remove another electron, the ionization energy will move, okay, for Mg, okay, Mg plus, Mg2 plus. But when I want to remove a third electron from Mg, there is a big jump. Okay, there is a big jump because there is going to be you are trying to remove from the inner shell. Okay, so you require a lot of energy. But for transition element, it's not like that. When I remove one electron from 3D, I remove another electron from 3D. I remove another electron from 4s. Remove another electron from 4s. Because why? The ionization energy is almost the same. Okay, similar. So there is no big jump. So that is the explanation why they say the similarity in the energy. Okay, and then the last one, this one is the bio stuff. Okay, you can actually look over here. I sent this work document also to you. You can have a look. Okay, 3 marks. Okay, what are the important things that you need to mention? Active site. Okay, substrate shape is complementary to the active site. When they bind, okay, when they bind, the substrate will start to actually lose the bond will become weakened, then the product is released. So the 3 marks, what are the points that they want? Active site, substrate shape is complementary to active site, okay, and then the bond is weakened. So please remember all this. 3 marks. It's very easy mark, yeah, to obtain. So the only thing that I didn't do today is going to be this one. Maybe quickly next lesson I can actually just go through this with you. Okay, but if you want to go through yourself, okay, this paper has been sent to you. Okay, my working paper, you can have a look. Okay, why I selected this. Okay, 3 marks. Okay, quite important. So anyway, okay, that's it for today. You can go for your lunch. Okay, any question before you go? Okay, so guys, you check the WhatsApp, okay, the one I sent, okay, the WhatsApp, the next question that I wanted to go through is going to be your paper 4.2, okay, 4.2. So please revise, okay, this one is going to be paper 4.1, 4.2 I gave last time, okay, so May, June, okay, 4.2, and if you have done, keep on going. Okay, so keep on going according to the WhatsApp group. So today I sent 2 more papers with the marking key. Okay, so you can actually check from there. Okay, any question, Jason? Okay, Gabriela, Nicole.
No, sir.
Okay, I can hear so many times someone leaving the room. Is it Janice? Yeah. Hey, I don't see Lavi. Lavi, are you here?
Sir,
Mm,
sir,
yeah.
Lawis internet is bad.
Okay. But was she here last time? Just now.
I think so.
Okay. Never mind. I'll just ask in the group. Yeah. So currently I have like Arneta is I have 2 accounts. Okay. So it means if I remove that, okay, I have 9 students. Only 2 students are missing. So Lavi and Janice. Yeah. Okay. That's all, guys. See you. Bye.